Over 500 million years ago, Earth looked nothing like it does today. Strange oceans, alien creatures, and the first complex life awakening beneath the waves. In this calm journey, we'll explore what our planet was truly like during the Cambrian period. If you enjoy it, please like, subscribe, and share, and tell us in the comments, which Cambrian creature would you love to see with your own eyes? Thank you for watching. Now let's begin. Around 541 million years ago, Earth turns slowly beneath a pale blue sky, veiled by thin layers of high cloud. The continents that exist in this distant time are unfamiliar in shape and placement. Vast Gondwana stretches across the southern hemisphere, an immense landmass ringed by shallow seas. To the north lie Laurentia Baltica and Siberia, smaller continents adrift upon the wide global ocean, known to later geologists as Panthalassa. Between them lies a scattering of microcontinents and island arcs, fragments of crust carried by slow-moving plates. The outlines of these lands are softened by erosion and tidal movement, with no forests or grasses to hold the soil in place. Bare rocks and sandstones glint under a sun slightly dimmer than the one known today, its light diffused through an atmosphere rich in carbon dioxide and low in oxygen. The air is heavier thick with volcanic gases that rise from frequent eruptions along the continental margins. Yet despite this, the climate is warm and stable. Ice is almost entirely absent from the poles, and the seas extend far inland across low-lying coasts. Sea levels stand high, because no permanent ice sheets store water on land. The warmth comes not only from solar radiation, but from the planet's internal heat. The crust continues to reshape itself as mantle convection drags the continents apart and closes ancient oceans. Ridges spread new seafloor, subduction zones pull crust downward. These movements are slow on human scales, yet constant enough that the geography of each 100 million years is renewed. The Cambrian world has just emerged from the final pulses of the Ediacaran, a time when multicellular life existed, but remained soft-bodied and rare. Now as the new eon begins, stability in temperature, chemistry and nutrient cycles allows ecosystems to expand. Sunlight strikes the oceans at a shallower angle near the poles, and more directly near the equator, generating slow circulation patterns that redistribute heat. Winds are gentler than those of later ages, because vegetation has not yet appeared to create strong gradients of humidity and drag. The land remains silent and empty, populated only by microbial films that darken wet surfaces, and perhaps thin colonies of lichen-like growths near shore. Across the continents, rivers flow sluggishly over naked stone, carving braided channels through loose sediments. These rivers deliver minerals to the sea, enriching shallow waters with calcium, silica and trace metals. Each rainfall carries fine dust that once settled into unbound soils now swept toward the coasts. Storms stir the margins of the continents but rarely reach the scale of modern hurricanes, for atmospheric dynamics are gentler and energy gradients smaller. The humidity is high, the air dense, the horizon often hazy under scattered volcanic aerosols. The oceans themselves are immense and ancient. They shimmer under the faint sun, their surfaces calm but their depth still poorly mixed. The uppermost layers are oxygenated through contact with the atmosphere and photosynthetic microbes, while deeper zones remain nearly anoxic. This gradient governs where life may thrive. In the shallows, microbial mats and drifting plankton proliferate, forming thin veils of colour when seen from above. Below a few tens of meters, light fades, and with it the range of active metabolism. Far beneath, along spreading ridges and volcanic vents, mineral-rich fluids emerge, sustaining small but steady chemosynthetic communities. Earth's magnetic field generated by the molten core is already strong enough to deflect most of the solar wind. Auroras shimmer near the poles, though no eyes exist to watch them. The day length is slightly shorter than in the present, perhaps 21 hours, because the moon is closer its gravitational pull, drawing stronger tides. These tides influence coastal habitats profoundly. Twice each short day, water surges across the margins, stirring sediments and redistributing nutrients. When the tides retreat, they leave rippled flats of silt, where microbial carpets glisten in the sun. The continents themselves differ in altitude and form. Gondwana stretches from the equator toward the southern pole, its interior highlands worn into plateaus by countless rainstorms. To the north, Laurentia sits near the equator, giving it tropical warmth and broad carbonate platforms ideal for early reefs. Baltica drifts farther north, experiencing cooler waters, while Siberia remains isolated, surrounded by deep basins. The positions of these continents affect ocean currents and the dispersal of species. Narrow seaways between them channel warm water into colder regions, spreading oxygen and life. Volcanism is a regular feature of the Cambrian Earth. Ash falls periodically upon both land and sea, enriching environments with nutrients while also altering local chemistry. Beneath the ocean, lava pours from ridges, cooling into dark basalt that forms the growing floor of Panthalassa. The heat flow from these processes drives hydrothermal systems that release metals and gases into the water column. Sulfides precipitate near vents, feeding microbial colonies that form the base of isolated ecosystems. Far above, plankton drift and multiply, transforming sunlight into organic matter that sinks slowly to the seafloor, linking surface energy to the deep. Atmospheric oxygen continues to rise, or it remains far below modern levels. The increase is gradual, shaped by photosynthetic organisms that release oxygen faster than it is consumed by oxidation of rocks. This slow accumulation allows larger, more complex life to flourish in the oceans. Yet on land, the concentration is still too low to support animal respiration. The surface remains barren, painted in muted tones of grey, brown, and red colours of iron oxides and weathered silicates. Only in coastal pools do biofilms create hints of green or purple. The skies are clear for long stretches of time, punctuated by weeks of volcanic haze or dust storms. Lightning flashes occasionally over warm seas, igniting nitrogen reactions that feed the nutrient cycles. Rain falls gently but frequently, washing aerosols back into the ocean. The global temperature hovers around 20 to 25 degrees Celsius, a uniform warmth that minimizes climate extremes. Without land plants, carbon dioxide concentrations remain high, and feedback mechanisms that later stabilize temperature are still weak. Nevertheless, the world remains in balance. Warmth begets evaporation. Evaporation returns as rain. From orbit, the Cambrian Earth would appear as a planet of blue and ochre, its oceans vast and streaked with pale sediment, plumes, its continents edged in shallow turquoise shelves. There are no ice caps, no forests, no deserts in the modern sense. The line between sea and land is fluid, changing as tides and tectonics slowly shift. Over the next tens of millions of years, this environment will host an extraordinary diversification of life, the Cambrian explosion. But at this moment, it is a tranquil and self-contained world. The surface glows under the young sun, the atmosphere hums with volcanic breath, and the ocean stirs softly beneath the pull of a nearer moon. Time moves quietly. The planet turns unhurried, balanced between heat and light, setting the stage for what will come without yet revealing it. Across the surface of Cambrian Earth, the arrangement of continents defines the planet's character as surely as its oceans and atmosphere. Gondwana dominates the southern hemisphere, a massive composite of what will one day become Africa, South America, Antarctica, Australia, and India. It stretches across a third of the globe, its edges submerged under warm shallow seas that lap gently over low continental slopes. Toward its centre lie arid uplands sculpted by wind and rain into broad plateaus and barren ridges. There are no plants or soils, only raw mineral surfaces polished by the elements. Rivers flow outward from these highlands, meandering through braided channels before fading into coastal lagoons. At the equator sits Laurentia, a smaller but influential landmass, corresponding to much of modern North America and Greenland. Its coastlines are rimmed with carbonate platforms that extend hundreds of kilometers into the sea, forming bright turquoise shelves visible from space. Warm tropical currents wash against these margins, sustaining dense microbial mats, and the first reef-like frameworks built by early sponges and archaeocyathans. To the northeast drifts Baltica, the ancestor of northern Europe, lying at higher latitudes where the sun rides lower in the sky. Its shores are cooler, its waters less saline, and its weather less stable. Occasional volcanic chains mark where oceanic crust sinks beneath continental margins, recycling material back into the mantle. Farther east, isolated and compact, stands Siberia, an independent microcontinent encircled by deep basins. It remains largely submerged, its submerged slopes home to early animal communities, adapted to dim light and moderate cold. Between these primary masses, countless microcontinents and island arcs wander upon the seafloor. Each one carries its own small ecosystem, a unique combination of sediments and volcanic terrain. Collisions between them are common, though they unfold over millions of years. When they meet, mountain chains rise briefly before erosion levels them again, feeding fresh minerals to the sea. The geometry of these moving plates determines the planet's circulation systems. Ocean currents snake between Gondwana and Laurentia, linking the hemispheres through equatorial passages that distribute heat. The prevailing pattern is one of gentle thermal equilibrium. Without polar ice temperature, gradients remain modest, so currents are steady rather than violent. The global climate resembles an endless early summer, humid and quiet. Along Gondwana's northern margin, shallow epiric seas extend far inland. Their waters shift slowly with each tide, creating vast tidal flats, where microbial mats trap sediment and form thin layers of carbonate. These platforms will someday lithify into limestones filled with fossils of trilobites and brachiopods, but in the Cambrian moment they are alive with unseen activity. The continents are not static. Subduction zones consume oceanic crust at their margins, while spreading centres create new seafloor. Volcanic arcs form in long chains parallel to the coasts, sending ash and lava into the sky. When eruptions subside, their remnants become fertile ground for chemical weathering, releasing nutrients like phosphorus and iron that drift into the oceans. The lack of vegetation allows erosion to proceed rapidly. Rainwater, slightly acidic with dissolved carbon dioxide, dissolves rock surfaces and carries ions downstream. In the process, it shapes the early landforms into rounded hills and smooth plains. The wind lifts fine dust from dry basins and scatters it across the lowlands, tinting the atmosphere a faint yellow on clear days. Over millions of years, this slow transport of sediments regulates the chemistry of the ocean, providing the raw materials for biomineralization, the process by which organisms form shells and skeletons. Each continent thus becomes both a supplier and an archive, feeding the ocean even as it records its own transformation. The interiors of Gondwana and Laurentia remain largely lifeless. Their landscapes are marked by contrasts of colour and texture, iron-red deserts, grey volcanic plateaus, pale carbonate flats. The absence of plants means that temperature swings sharply between day and night. Winds cross these surfaces unhindered, whistling through empty valleys and over basalt ridges. Occasional shallow lakes form in depressions after rainfall turning green with microbial films before evaporating into cracked mud. Lightning storms flash across the highlands, releasing nitric oxides into the air that later dissolve into rain and enrich coastal waters. Every process on land eventually returns to the sea, for the biosphere of this age is almost entirely marine. Viewed from above, Gondwana's outline resembles a broken crescent curved around a deep equatorial gulf. The sunlit waters at its edges are dotted with carbonate platforms, while its southern reaches approach cooler, dimmer latitudes. In those regions, glacial remnants from the late Proterozoic have long melted, leaving broad continental shelves where cold currents meet warmer flows from the north. These intersections produce upwellings of nutrients that sustain plankton blooms. The atmosphere above is dense with water vapor, but weather patterns remain simple, slow-moving fronts and gentle precipitation rather than violent storms. Without complex vegetation, there are no forests to trap humidity, no roots to channel rainfall into rivers. Instead, water runs directly over stone-carving ephemeral channels that change course after every storm season. Laurentia, smaller but crucial, serves as a pivot in the global circulation system. Its equatorial position exposes it to the most direct sunlight, creating expansive carbonate banks that act as chemical buffers for the ocean. These banks help regulate acidity, stabilizing the marine environment. Over time, they will become thick successions of limestone, capturing in their layers the remains of organisms that flourish in the warm Cambrian shallows. In contrast, Baltica and Siberia occupy cooler zones. Their marine shelves are narrower, their sediments dominated by silts and muds rather than carbonates. Yet they too nurture distinct communities of early life organisms adapted to lower temperatures and higher turbidity. The dynamic balance among these continents defines the Cambrian landscape. Tectonic drift continues at a steady pace of a few centimetres per year, imperceptible on a daily scale but decisive over geologic time. Collisions and rifts periodically alter the map, closing ancient basins and opening new ones. Each change in geography modifies the flow of the oceans, influencing oxygen levels, nutrient cycles, and the spread of species. The world of the Cambrian is therefore not static, but rhythmically alive with movement, though its tempo remains too slow for any observer to notice. Earth's magnetic poles wander across the surface, shifting in response to convection in the core. This wandering leaves faint imprints in iron-bearing rocks that future geologists will use to reconstruct the dance of continents. But within this era, the process is invisible, a silent choreography shaping the deep time architecture of the planet. The continents drift under a sun that burns a little dimmer than today's, casting a softer light across seas of jade and silver. There are no trees, no birds, no footprints on the sand. Only wind, water, and stone define the scenery. Yet within the margins of these continents, where the land meets the sea, chemical gradients and stable warmth create the conditions that will soon ignite biological innovation. In every direction, the Cambrian world breathes slowly. Gondwana sprawls like a sleeping giant across the southern hemisphere. Laurentia, Baltica, and Siberia drift apart under the pull of unseen forces. Between them, the Panthalassic Ocean spreads its wide, silent expanse. The continents rise and sink over eons, but for now they rest under gentle skies surrounded by warm, clear waters. This quiet geometry of land and sea forms the foundation upon which all later Cambrian life will depend, a planet balanced, patient, and alive in ways still hidden beneath the waves. The climate of the Cambrian Earth is one of enduring warmth and remarkable stability. Global temperatures remain consistently high, and even the polar regions escape long-term ice. The absence of permanent glaciers means that sea levels are elevated worldwide, flooding continental margins and creating shallow epicontinental seas that stretch across much of Gondwana, Laurentia and Baltica. This broad coverage of shallow marine environments defines the tone of the age, a planet of warm oceans, gentle tides and wide coastal shelves teeming with primitive life. The warmth comes from several intertwined sources. Volcanic outgassing continues to enrich the atmosphere with carbon dioxide trapping, solar radiation, more effectively than in later eons. The sun itself shines slightly weaker than in the present, but the thick greenhouse blanket compensates for that dimness, producing an even moist heat that extends from equator to pole. The ocean surface temperature may average between 20 and 30 degrees Celsius, decreasing gradually with latitude but never dropping low enough to freeze. In this stable climate, evaporation is constant, rainfall abundant, and circulation systems gentle yet efficient. The chemistry of the atmosphere and ocean is unlike that of later ages. Oxygen levels have been rising since the Proterozoic, but they still hover well below modern values, perhaps no more than a tenth of what they will one day reach. The lower atmosphere is dense with nitrogen, water vapor, carbon dioxide, and trace gases such as methane and sulfur dioxide. This mixture maintains high humidity and enhances the scattering of sunlight, creating a diffuse brightness even on clear days. Clouds form readily over warm seas, drifting slowly across latitude, shedding light rain that returns nutrients to the ocean. There are no forests to moderate the carbon cycle, no roots to store carbon in soil. Instead, carbon moves directly between air, rock and water through weathering and sedimentation. Each raindrop that falls on a continental surface reacts with exposed minerals, dissolving carbon dioxide and carrying calcium, magnesium and bicarbonate ions toward the sea. Once these ions reach the ocean, they participate in a delicate chemical balance that defines marine life. The seawater of the Cambrian is rich in dissolved calcium and silica, a combination ideal for the formation of shells and skeletons. Carbonate saturation levels are high, enabling organisms to secrete calcium carbonate with relative ease. This chemical condition becomes a crucial foundation for the biological revolution of the era, allowing animals to develop hard parts that can endure and be fossilized. However, the chemistry is not uniform everywhere. In shallow tropical regions where evaporation exceeds precipitation, salinity rises and the concentration of minerals increases. In deeper or cooler basins where circulation is limited, water becomes depleted in oxygen and slightly acidic, leading to zones of low habitability. These gradients create distinct habitats across the marine realm, from well-oxygenated reefs near the surface to dark, stagnant basins at depth. The circulation of the oceans is driven by temperature differences and by the steady pull of tides from a closer moon. Surface currents transport warm, oxygen-rich water from the equator toward the poles, while deep return flows move colder, denser water back toward the tropics. This slow conveyor distributes nutrients and stabilizes the climate. Because continental configurations restrict the free movement of water, local basins often develop independent circulation systems, forming miniature oceans with their own chemistry and ecology. At times, restricted basins become anoxic, accumulating black muds rich in organic material that will later form shales and other sedimentary records of life. These oxygen-poor layers act as both cradle and archive for the developing biosphere. The interaction between atmosphere and ocean shapes the color and clarity of the Cambrian seas. High concentrations of plankton and dissolved minerals lend the water a blue-green hue, especially over carbonate platforms. Sunlight penetrates deeply in clear equatorial zones, while near coasts suspended sediments give the water a milky or turquoise tone. The upper layers teem with photosynthetic microorganisms that release oxygen into the surrounding medium. Although their contribution to the global atmosphere is slow, they steadily increase the oxygen concentration in surface waters, supporting more active metabolisms. Beneath this layer, at depths beyond 100 meters, oxygen dwindles, and the water takes on a darker, more stagnant character. Hydrogen sulfide may accumulate in extreme cases, creating toxic zones, where few organisms survive. The contrast between these layers generates a vertical mosaic of habitats that define the structure of early marine ecosystems. Carbon dioxide levels in the air remain high, perhaps 20 times modern concentrations. This enhances the greenhouse effect but also ensures that chemical weathering on land proceeds rapidly. The dissolution of silicate rocks removes carbon dioxide from the atmosphere and delivers bicarbonate ions to the ocean, providing raw material for carbonate deposition. This feedback loop stabilizes temperature over geological timescales, increased warmth, accelerates weathering, which then draws down carbon dioxide, moderating the greenhouse effect. The system achieves a natural equilibrium that maintains long-term warmth without runaway heating. It is a world balanced between volcanic input and chemical output between the sky's gases and the ocean's minerals. Storms occur frequently over the seas, though they are rarely catastrophic. Warm air rising from the ocean surface condenses into bands of cloud that release steady rain rather than violent downpours. The waves that accompany these storms stir sediments along continental shelves, mixing oxygen into the water column and redistributing nutrients. When the winds calm, particles settle again, layering the seabed with fine deposits that will harden into sandstone and shale. The rhythm of weather thus becomes a geological instrument shaping the record of the Cambrian as it unfolds. The chemistry of life is also influenced by trace elements that circulate through this oceanic system. Iron, manganese, and phosphorus derived from volcanic sources and eroded continental crust enrich the water, stimulating biological productivity. Yet in areas where oxygen is low, iron remains in solution, giving the deeper waters a greenish tint. When these waters upwell to the surface, the sudden contact with oxygen causes the iron to precipitate as reddish oxides that settle back to the seafloor. Over millions of years, this cycle produces thin layers of iron-rich sediments that mark transitions between oxygenated and anoxic conditions. Each band becomes a time-stamped signal of the shifting chemistry of Earth's early oceans. Despite the heat and humidity, the planet's overall climate remains remarkably uniform. Without land vegetation, there are no strong seasonal contrasts or continental interiors to trap heat. The result is a stable global environment, warm and calm enough to nurture the evolutionary experiments of the Cambrian seas. The atmosphere glows faintly at sunrise, tinged with the colors of volcanic aerosols. The ocean reflects that light in muted shades of gold and teal. Across this planet, energy moves slowly, diffused through water and air rather than concentrated in storms or glaciers. The air smells faintly of sulfur near volcanic chains and of salt near the coasts. Each breeze carries moisture from the sea, each tide moves nutrients from one realm to another. The Cambrian earth breathes through its oceans, exhaling gases, inhaling minerals, maintaining equilibrium through endless circulation. Beneath its calm surface, chemistry becomes the silent architect of life. Carbon, calcium, and oxygen bind and separate in continuous cycles, laying the invisible groundwork for skeletons, shells, and reefs. Every ripple, every drop of rain, every grain of sediment participates in this vast chemical conversation. It is within this steady warmth and balance that evolution will soon take its greatest leap, but for now the world drifts in quiet harmony, a planet of warm seas, soft light and air heavy with the breath of its own making. Along the edges of Gondwana, Laurentia Baltica and Siberia, the shallow seas of the Cambrian stretch in broad, tranquil expanses that seem almost endless. Here the continents taper into continental shelves, submerged beneath only a few tens of meters of water. The sunlight reaches the seafloor with ease, warming the sediments and sustaining an intricate web of microbial life. The water is clear, tinted blue-green by plankton and dissolved minerals. Each tide transforms the landscape, flooding and draining wide flats of sand and carbonate mud. These gentle movements of water, governed by the pull of a closer moon and steady planetary rotation, establish the daily rhythm of this world. Twice each short day the ocean advances and retreats, sculpting ripple marks carrying fine silt and leaving behind gleaming sheets of wet sediment that capture the traces of moving creatures. The seafloor of these shallow margins is varied and dynamic. In some regions, broad carbonate platforms dominate, built from lime mud precipitated directly from seawater. Elsewhere, quartz sands derived from continental erosion spread outward from deltas, their grains rounded and polished by waves. Thin layers of clay settle in quieter areas, forming smooth, dark patches between rippled fields of sand. Across all of these surfaces, microbial mats grow in sheets, binding sediment grains together and stabilizing the terrain. These mats consist of cyanobacteria and other photosynthetic microbes that trap particles and secrete sticky films, turning unstable sand into cohesive crusts. Over time, the mats produce fine laminations that will harden into stromatolites layered structures, marking the presence of life on an otherwise barren seafloor. The atmosphere above these seas is warm and moist, the air filled with the scent of salt and trace gases from nearby volcanoes. Gentle winds stir the surface, creating small waves that shimmer under the high Cambrian sun. The sky is pale, with clouds forming in long, thin strands that drift eastward, breaking the light into soft glows across the water. Rainfall is frequent, but light returning evaporated moisture to the ocean in a closed cycle that keeps salinity roughly stable. The absence of land plants means that rivers entering the sea carry few organic materials, but they deliver abundant minerals from the continents. Calcium, magnesium and silica flow continually from weathered rock, enriching the nearshore waters and sustaining the process of biomineralization that defines this age. Where the sea meets land, tidal flats extend for kilometers. During high tide, they are covered by shallow water alive with plankton and drifting detritus. During low tide, they glisten under the sun, thin films of moisture reflecting the bright sky. Microbial carpets colonize these flats, forming dark gelatinous layers that breathe oxygen into the thin water. Within them, bubbles of gas collect beneath the surface and burst softly as the tide returns. Occasionally, primitive animals, worm-like burrowers, early arthropods and other soft-bodied forms cross these zones, leaving faint trails in the mud. Most of these creatures remain hidden during low water, retreating into burrows or beneath the mats where moisture persists. Their presence hints at the slow rise of mobility and predation, two forces that will soon reshape marine life completely. The chemistry of these shallow waters is delicately balanced. Sunlight penetrates deeply enough to support photosynthesis across the entire shelf, yet the warmth of the surface promotes strong evaporation. The combination increases salinity, especially in enclosed lagoons or restricted bays. Where salinity grows too high, only microbes can survive, forming crusts of halite and gypsum that glitter like frost in the tropical heat. Elsewhere, gentle circulation maintains oxygen levels, allowing soft-bodied animals to thrive in surprising numbers. The interplay of evaporation, precipitation, and tidal exchange governs which regions become nurseries of life, and which become barren salt pans. Across vast stretches of the Cambrian world, reefs begin to appear for the first time in Earth's history. These are not the coral reefs of later ages, but frameworks built primarily by archaeocyathans, cup-shaped sponge-like animals with calcareous skeletons, and by microbial organisms that cement sediments together. The reefs grow in belts parallel to coastlines rising a few meters above the surrounding seafloor. Their surfaces teem with algae, sponges, and small grazing animals that cling to the hard substrate. Between the reef mounds, channels carry clearer, cooler water that mixes with the warmer shallows, regulating temperature and chemistry. These environments become centers of biodiversity, anchoring ecosystems that depend on structure and stability. The sedimentation processes of these margins unfold in slow motion. Each tide deposits a thin layer of grains. Each storm reworks the upper few centimeters of the seabed. Over millions of years, this repetition builds thick sequences of sandstone, shale, and limestone that record the rhythm of Cambrian seas. In cross-section, these layers appear as delicate alternations of light and dark bands, evidence of subtle shifts in current salinity and biological activity. In the stillness of this world, time accumulates as sediment, each particle, a fragment of rock shell or microbial film. The energy of the system is low, yet its persistence is absolute. Nothing remains unchanged for long, but nothing changes suddenly either. The clarity of the water allows sunlight to reach surprising depths, creating a gradient of color from bright turquoise near shore to deep blue farther out. In the uppermost layers, plankton absorb light and produce oxygen. Just below, the concentration of oxygen decreases as respiration and decay consume it. At the boundary between these layers, chemical reactions transform dissolved iron and sulfur, producing thin greenish clouds that drift slowly in the current. These gradients of chemistry mirror the gradients of life-shaping where organisms can survive. The shallows are lively, the mid-depths quieter, the deeper zones nearly still. When storms sweep in from the open ocean, the calm equilibrium of the margins is briefly disturbed. Strong winds push waves onto the shore, eroding reefs and stirring sediments. Particles remain suspended for days, turning the clear water into a haze. Yet even these disturbances serve a purpose. They mix nutrients from deeper layers into the photic zone, renewing productivity and redistributing life. After the storm passes, the sea clears and the process begins again. The Cambrian Ocean is a closed loop of renewal, a self-regulating system where destruction and creation operate side by side in gentle rhythm. In some regions, underwater dunes of sand migrate slowly across the shelf, driven by currents. Their crests ripple under the constant movement of water, creating patterns that repeat for thousands of years. Between the dunes, quieter basins collect fine muds rich in organic material. These contrasting environments, energetic and still bright and dim, exist within sight of each other, forming a mosaic of habitats. Life adapts to every niche, spreading wherever chemistry and light permit. The ocean floor becomes a living surface textured by both biology and geology. From a planetary perspective, these shallow margins form glowing rings of turquoise around the continents. Viewed from space, they appear as luminous bands separating the darker ocean from the brown and red interiors of land. They are the transition zones where continents breathe into the sea, where the raw materials of the earth dissolve into forms that sustain life. Each wave that breaks on these early shores carries dust from the continents and returns it transformed atoms of calcium bound into shells, grains of silica locked into the skeletons of sponges, fragments of carbon stored within limestone. The cycle is endless, slow and precise. As the Cambrian continues, these margins will remain the stage upon which most life unfolds quiet and gleaming under a patient sun. At the uppermost skin of the Cambrian Ocean, sunlight scatters through the clear blue surface, transforming the water into a living lens. This thin layer, only a few tens of meters deep, supports an entire world of drifting organisms that depend on light. Each photon that enters the water triggers a quiet chain of reactions sustaining the global balance of oxygen and carbon. The ocean's surface shimmers, continuously disturbed only by gentle winds and the steady rise and fall of tides. There are no continents nearby to cast shadows or deliver heavy sediments, and the clarity allows light to penetrate deeper than in most later ages. The result is a bright glowing ocean top, where the first complex marine ecosystems emerge and evolve. The air above is moist, the temperature steady, the horizon veiled by distant haze. From the surface, the water appears almost motionless, but beneath that calm countless organisms drift in slow, perpetual motion. The surface waters host microscopic architects of planetary change, cyanobacteria, green algae, and a growing diversity of single-celled eukaryotes. These tiny forms float freely, absorbing sunlight and carbon dioxide to build organic matter. Their pigments capture blue and red wavelengths, leaving the sea tinted turquoise. As they photosynthesize, they release oxygen, which dissolves into the water and diffuses into the atmosphere. This process, occurring invisibly billions of times each second, continues across every ocean basin, turning the Cambrian Earth into a more breathable planet. The concentration of oxygen near the surface rises slowly, supporting new metabolic possibilities for multicellular organisms that graze upon these microscopic producers. Though no creature can yet leave the sea, this layer of light becomes the cradle of nearly all biological energy that sustains the marine world below. Tiny planktonic cells congregate near the boundary where light and nutrients intersect. The balance between photosynthesis and the pull of gravity defines their lives. When nutrients are scarce at the surface, currents or upwellings from below bring renewed supplies of phosphorus, nitrogen, and iron. These nutrients sustain blooms of plankton that drift with the currents, their populations waxing and waning with the rhythm of the sea. In turn, small filter-feeding animals rise toward these blooms, capturing particles with delicate appendages or nets of mucus. Their transparent bodies, often less than a few millimeters long, move almost imperceptibly. They swim or sink, carried by the water, living and dying in the same slow cycle that defines the Cambrian Ocean. The physical character of these surface waters reflects the planet's chemistry. The temperature remains warm across latitudes, rarely dropping below 20 degrees Celsius. The density gradient between surface and deeper layers forms a subtle barrier that limits vertical mixing. As a result, most biological activity occurs in the uppermost band of light. Beneath it, the ocean darkens rapidly, and life thins to near invisibility. The clarity of the water allows sunlight to reach depths beyond 50 meters in equatorial regions, but productivity decreases sharply below the photic zone. Even so, the slow sinking of organic particles, dead plankton, fecal matter, and dissolved carbon connects this illuminated world to the darker depths, nourishing benthic life and driving global cycles of energy. Storms occasionally disturb the serenity. When winds strengthen waves, overturn the upper layers, blending oxygen and nutrients. The sea becomes clouded with microscopic debris, scattering light into a soft green glow. After the storm, the plankton populations recover quickly, multiplying in the enriched conditions. The gentle equilibrium returns, and for long stretches of time the ocean surface remains undisturbed except for slow swells. In these periods of calm, countless microcurrents twist and merge, creating patterns of motion invisible from above, but vital to the distribution of life. The interplay of light and matter shapes not only the chemistry, but also the visual texture of the Cambrian Sea. In the morning, the water takes on pale tones of gold and blue. By midday, it turns bright turquoise, reflecting the high sun. By evening, it fades into silver grey under the soft glow of scattered light. The moon's reflection traces long paths across the surface during the shorter Cambrian nights, and tides create rhythmic zones of mixing that pulse with biological activity. Each day and night cycle renews the balance between photosynthesis and respiration, between the capture of energy and its return to the ocean. Within this illuminated domain, the earliest planktonic animals appear. These creatures, some resembling minute crustaceans, move through the water column, feeding on single-celled algae. Others drift passively, relying on appendages or filaments to slow their sinking. Many are transparent, allowing sunlight to pass through their bodies, a natural camouflage in the luminous sea. Predation, though still primitive, begins here. Small swimmers consume smaller ones, introducing a new level of complexity into the food web. Every organism in this system participates in cycles of energy transfer that will echo throughout all future oceans. Occasionally near volcanic islands or shallow shelves, mineral-rich springs release gases and trace elements into the surface water. The sudden influx of iron triggers brief surges of productivity, darkening patches of the sea with dense blooms of plankton. From above these regions appear as shifting stains of green and brown amid the blue expanse. The organisms within them grow rapidly and die just as fast falling to the seafloor as a slow rain of organic matter. This invisible snowfall carries the energy of the surface into the deep linking distant environments in a single global circulation. The water itself is in constant gentle motion. Winds drive long, slow waves that move across thousands of kilometers without breaking. These waves transmit energy, without transporting much water, maintaining the surface equilibrium. Beneath them, internal waves ripple along density boundaries unseen but powerful, mixing the layers over time. The soundscape of this ocean is quiet, no surf, no rain, only the faint hum of movement and the occasional whisper of bubbles rising from photosynthetic mats near the surface. The interaction of sunlight with particulate matter gives the ocean a faint glow even at night. Bioluminescence, still rare, begins to emerge among some planktonic organisms, tiny flashes of green light released in response to mechanical disturbance. These first sparks of biological illumination serve no clear purpose yet but prefigure the visual wonders of later oceans. They flicker briefly under moonlight and vanish, leaving the surface calm once more. The upper ocean during the Cambrian thus functions as both laboratory and engine. Here energy from the sun enters the biosphere. Here oxygen is released. Here the foundation of all marine ecosystems takes form. Every molecule of carbon fixed by plankton supports the gradual expansion of complex life. The thin boundary between air and sea becomes the interface through which the planet breathes. The cycle is ceaseless and nearly silent. There are no seasons in the modern sense, no migrations across continents, only continuous transformation. Over millions of years, the balance between light chemistry and motion defines the stability of the entire biosphere. Seen from orbit, the surface waters of Cambrian Earth gleam in soft gradients of colour. Turquoise near continental shelves, deep indigo in open basins, and pearlescent white where light strikes clouds or shallow sands. From this luminous film, life draws its first organized strength. Everything beneath depends on it. The reefs that rise on the shelves, the creatures that crawl upon the mud, the animals that swim in the middle depths. The calm expanse of water under the high Cambrian sun is therefore more than a habitat. It is the living skin of the planet constantly renewing itself, carrying light downward into time. Beneath the radiant surface of the Cambrian Ocean, light begins to weaken, and the colours shift from turquoise to deepening blue. Here, between 50 and 200 metres below the surface, the world grows dim and slow. Sunlight fades into a pale glow, scattering into long beams that move with the gentle swell of the water. The temperature drops gradually a few degrees cooler than the surface, but still warm enough to sustain life. The currents are sluggish, moving like great underwater rivers that carry suspended particles from one basin to another. This zone, neither fully bright nor completely dark, marks a boundary between two realms. Above lies the energy of photosynthesis and constant renewal, and below stretches the stillness of near-permanent shadow. It is within this middle layer that the quiet balance of the Cambrian Ocean is maintained. Oxygen levels in these depths are lower than near the surface. The living plankton above produce oxygen by day, but much of it is consumed here by the slow decomposition of sinking organic matter. The result is a stable but delicate equilibrium, enough oxygen to sustain small animals yet always near depletion. In regions where circulation falters, oxygen can vanish entirely, and anoxia spreads like a silent fog along the slopes of the continental shelf. Chemical reactions take over, where biology retreats. Sulfur compounds replace oxygen in sustaining microbial processes, creating invisible gradients that separate one form of life from another. The transition between oxygenated and anoxic water is subtle, measured not in abrupt layers, but in slow blending zones that shift with seasons, tides, and currents. The inhabitants of these depths live in permanent twilight. Small swimmers, perhaps early arthropods and primitive crustaceans, move slowly through the water column, feeding on the steady rain of dead plankton and detritus. Their translucent bodies are adapted to low light with simple eyes, or light-sensitive patches that detect brightness rather than detail. Many drift rather than swim, conserving energy in a world where food arrives sporadically from above. Some species float with the help of oil-filled chambers or spiny extensions that slow their sinking. Others are weak swimmers that pulse or glide in slow arcs, tracing the invisible boundaries between light and shadow. Predation exists here, but it is measured and rare, swift ambushes followed by long intervals of drifting. Energy is scarce and survival depends on restraint. The faint light that reaches these depths sets the tone of the entire environment. Every colour except blue is absorbed by the water. Red vanishes first, then orange, then green. The creatures that inhabit this layer are pale, sometimes transparent, sometimes faintly tinted with blue or violet hues that merge with the water around them. The absence of bright colour makes movement almost invisible, and stillness becomes a natural form of defence. Occasionally weak flashes of bioluminescence pulse across the darkness, caused by microorganisms that release light when disturbed. These brief glimmers travel only a short distance before fading, marking tiny acts of interaction in a vast, silent space. The chemistry of the middle depths mirrors its slow rhythm. Carbon dioxide increases with depth, produced by the respiration of decomposers and the oxidation of sinking organic matter. The water becomes slightly more acidic, dissolving calcium carbonate from tiny shells that drift down from the photic zone. In return, nutrients such as phosphorus and nitrogen accumulate, waiting for the rare currents or upwellings that will bring them back to the surface. This vertical exchange binds the ocean into one continuous system, Every organism that lives here is part of that cycle, feeding on what descends, releasing what will rise again. The deep ocean acts as a quiet archive of the surface, storing the byproducts of photosynthesis until the planet's circulation calls them upward. In regions near the edges of continents, the middle depths brush against the tops of submarine slopes and plateaus. Here water movement is slightly stronger. Internal waves generated by tides and density contrasts ripple along these slopes, stirring the sediment and mixing oxygen into the lower layers. These motions are invisible from above, yet they prevent stagnation and support communities of filter-feeding organisms that anchor themselves to rocky outcrops. Primitive sponges, early echinoderms, and soft corals extend their bodies into the passing currents, capturing fine particles drifting by. The light that reaches them is dim but steady enough to define shapes without casting shadows. Around them, trails of detritus descend slowly from the world above a gentle snow of organic material that nourishes everything that lives below. Occasional volcanic activity on the seafloor adds heat and minerals to these waters. Hydrothermal vents, though fewer than in later times, release warm metal-rich fluids that disperse into the surrounding sea. The minerals they carry, iron, manganese, sulfur, interact with seawater chemistry, creating gradients that support specialized microbial communities. These microbes form the base of localized food webs independent of sunlight, relying on chemical energy rather than photosynthesis. In these isolated systems, life persists entirely on geologic metabolism, sustained by the Earth's internal heat. Even so, most of the middle depths remain linked to the surface world through the slow descent of organic debris. The pressure here is higher than at the surface, but still moderate compared to the deep ocean. Water temperature and density stabilize into nearly uniform values, minimizing turbulence. The resulting stillness allows particles to settle gently onto the seafloor, where they accumulate in fine layers that will over time record each pulse of productivity and each volcanic eruption. In certain basins, these layers are perfectly preserved, undisturbed for millions of years. They become the future rock record of the Cambrian, storing traces of carbon, oxygen, and sulfur that tell the story of a living ocean breathing in its own rhythm. Sound travels efficiently through these waters, but few sources disturb the quiet. The only continuous noise is the low-frequency hum of distant volcanic activity and the faint crackle of chemical reactions near vents. No large predators churn the water, no shoals of fish break the calm. This ocean is not empty but restrained. Its energy is stored in chemical gradients, slow currents, and microscopic interactions. Time in this realm feels stretched. Processes that seem fleeting near the surface unfold here over weeks or months. The sinking of a particle, the decomposition of an organism, the mixing of a current, each happens at the scale of patience. Farther from the continents, where the open ocean deepens, the middle depths expand into vast twilight plains. These regions may stretch thousands of kilometers across, uninterrupted by land. The surface above glows faintly during the day and reflects starlight at night, but little of that reaches this far down. The organisms that live here drift freely, unbound by any fixed location. They are travelers of the dim blue world, sustained by the invisible connection between the energy of light above and the chemistry of decay below. In this quiet zone, the Cambrian Ocean finds equilibrium. The surface produces, the deep consumes, and between them the middle depths mediate. Every molecule of carbon and oxygen that circulates through this layer contributes to the long-term balance of the planet. It is a realm of fading light, but constant continuity, a slow exchange between life and the elements. If one could watch without interruption, one would see the entire ocean breathe, rising and falling, mixing and settling without pause, without haste. The fading blue of the middle depths holds the memory of light and the promise of renewal, linking the radiant surface to the unseen world below. Far below the luminous surface and the dim blue depths, the seafloor of the Cambrian continental shelf stretches outward in stillness. The water here is calm, its movement slow and deliberate, guided more by tides and long-term currents than by waves or storms. Light no longer penetrates with strength. Colours fade into muted greys and greenish shadows, and temperature stabilizes a few degrees cooler than above. This quiet world, though dark, is not lifeless. It is the archive of the planet where each grain of sediment, each layer of mud, and each chemical trace carries the story of oceans, continents, and living things. Every moment, microscopic particles fall from above shell fragments. Plankton remains mineral dust from volcanoes and silt carried from the continents. The descent is silent, a constant rain of matter that never stops layering the seafloor in increments too small to measure in human time. The sediments of the continental shelf are soft, fine, and oxygen-poor. In the shallowest regions, where water still circulates enough to reach the bottom, the surface muds are oxidized, taking on faint reddish or brown tones. Slightly deeper, where oxygen thins, the sediment turns grey, then black as organic material accumulates faster than it can decay. In these zones, bacteria dominate the chemistry. They break down organic matter in the absence of oxygen, releasing hydrogen sulfide and methane into the surrounding water. The result is a subtle but pervasive gradient, upper layers faintly oxygenated, deeper ones anoxic. This stratification creates the conditions that preserve fossils and chemical signatures across millions of years. Where life thrives near the surface, death and burial record it below. The topmost few centimeters of mud form a living skin populated by microbes. These invisible communities process carbon, sulfur, and nitrogen, converting decaying matter into minerals and gases. The process is slow but continuous. Each bacterial cell divides, consumes, and is replaced, maintaining a fragile balance that stabilizes the chemical environment. Occasionally, small animals disturb the surface burrowers that crawl or dig in search of food. Their movements mix oxygen into the sediment, sustaining more aerobic reactions. The traces they leave behind, tiny tunnels, tracks and mounds, are among the first complex patterns of behavior ever imprinted on Earth's geology. These simple marks preserved in stone will one day reveal to distant observers that life once moved through this quiet world. The floor of the Cambrian shelf slopes gently away from the continents, descending toward the deeper basins. Its topography is irregular but subdued, shaped by currents and by the slow accumulation of sediment rather than by tectonic upheaval. In some places, mounds of lime mud rise where microbial mats once flourished. In others, ripple marks record the shifting of sand under weak currents. Where storms reach this far, they stir the uppermost layer of mud, leaving subtle laminae that harden into sandstone over time. Between disturbances, the sea returns to stillness, allowing delicate layers to form undisturbed for centuries. This alternation of calm and motion, of deposition and reworking, produces the rhythmic patterns that later generations will recognize as the pulse of an ancient sea. Chemical reactions within the sediment proceed at a glacial pace. Iron and manganese oxides dissolve and reform pyrite crystals, grow in black layers where sulfur and iron combine. Tiny shells of calcium carbonate dissolve under pressure and reprecipitate as cement-binding grains into rock. Each process contributes to the slow transformation of soft mud into solid stone. This cycle of burial and lithification begins here beneath water that moves like breath. The geological future of the planet, its shales, limestones and sandstones, takes shape, molecule by molecule, in this unbroken darkness. Life at this depth is sparse but persistent. Worm-like creatures burrow through the upper sediment, leaving faint trails. Small trilobites crawl slowly across the mud, searching for decaying matter. Their eyes, adapted to dim light, perceive only brightness and shadow. They move methodically, pausing, often sensing chemical cues rather than sight. Some species gather near patches of microbial mat, grazing gently on the film of bacteria that coats the seafloor. Others live within the mud itself, filtering the water that seeps through. Each organism plays a role in stirring, mixing and recycling material. Though the density of life here is low, its influence on the environment is immense. The bioturbation caused by these creatures aerates, the sediment shapes its texture, and determines what will be preserved. The stillness of the water belies its complexity. Near the seafloor, thin boundary layers separate moving currents from resting sediment. Nutrients released by decomposition diffuse upward, fueling plankton in the photic zone far above. In return, organic debris drifts downward, feeding the communities below. This vertical exchange forms the heartbeat of the ocean, an invisible link connecting light and darkness. No single organism perceives the full system, but collectively they sustain it. The entire shelf operates as a slow engine of circulation, driven not by motion but by chemistry. Occasionally the balance is disrupted. A major storm on the surface can generate waves strong enough to stir the seabed, even at considerable depth. The fine sediment lifts into suspension, clouding the water and spreading across the shelf in thin, turbulent plumes. As the storm subsides, particles settle again, creating new layers that bury whatever lay beneath. These rapid burial events preserve extraordinary detail, the imprints of shells, the trails of burrowers, even the outlines of soft-bodied creatures. Such episodes are rare but transformative, recording the dynamic moments of the Cambrian world amid its long, quiet intervals. The shelf edge marks the transition between this tranquil plain and the steep descent into the abyssal ocean. Their gravity occasionally triggers submarine landslides, sending cascades of sediment tumbling down the continental slope. These events redistribute material from the shallow seas to the deep basins, ensuring that nutrients and minerals circulate across the entire marine system. Even in stillness, the planet remains in motion. Erosion, deposition and transport operate in harmony, maintaining equilibrium over millions of years. The chemical imprint of this environment extends beyond its sediments. The surrounding water absorbs ions released from decaying organic matter, altering its composition slightly as it moves across the shelf. Trace metals such as iron, copper and zinc accumulate, enriching nearby ecosystems. In regions where oxygen levels fall to zero, sulfate-reducing bacteria convert sulfur into sulfides, forming dark mineral crusts. These processes lock away carbon and sulfur in solid form, influencing atmospheric composition on a planetary scale. The seafloor thus acts not only as a record but as a regulator, mediating exchanges between the living world and the geological one. In the vast darkness of the Cambrian shelf floor, time seems to stretch endlessly. The slow drift of sediment, the quiet respiration of microbes, the unhurried movement of small animals all merge into one continuous rhythm. No sudden event disturbs the calm for centuries. Each layer of mud settles gently upon the next, compressing under its own weight, becoming history grain by grain. If one could listen closely, the only sound would be the faint hiss of water flowing through pores in the sediment, the whisper of chemistry unfolding in silence. Above, sunlight still dances on the surface, storms rage and tides shift, but here everything remains steady, indifferent, and patient. This is the planet's memory chamber, where light becomes stone and motion becomes form. The seafloor of the Cambrian shelf holds the beginning of Earth's written record, waiting quietly in darkness for the slow hand of time to turn it to rock. Within the shallow sunlit waters along the Cambrian continental margin, structures begin to rise from the seafloor. Small at first irregular mounds of lime and microbial film, but over time becoming complex frameworks that reach upward toward the light. These are the first true reefs built not by corals or modern sponges, but by organisms entirely new to Earth's architecture. The main builders are the archaeocyathans, cup-shaped animals with rigid walls of calcium carbonate, each resembling a hollow vase or a nested cone. Their skeletons form porous lattices that allow water to circulate freely through their bodies, filtering food particles from the surrounding sea. When they die, their remains accumulate cemented together by lime-secreting microbes that coat every surface. Layer upon layer, these bodies and microbial crusts build towering reef mounds that rise several meters above the seafloor. The result is a landscape unlike any the planet has seen before, a mosaic of limestone towers, caves and passageways where life finds both shelter and stability. The conditions that allow these reefs to flourish are precise. The water must be warm, clear and rich in calcium carbonate but low in sediment. Strong sunlight ensures the productivity of photosynthetic microbes that live symbiotically with the reef framework. Gentle currents bring a steady supply of oxygen and nutrients while preventing stagnation. These reefs develop mainly along the tropical margins of Laurentia and Gondwana, where equatorial seas maintain temperatures around 25 degrees Celsius. The clarity of the water allows sunlight to penetrate several tens of meters, illuminating the upper surfaces with diffuse blue light. Each archaeocyathon colony grows slowly upward and outward, leaving behind internal cavities that become microhabitats for other organisms, sponges, algae worms, and small arthropods. The reef environment transforms the physical landscape of the Cambrian Ocean. Where once the seafloor was soft and featureless, it now becomes a three-dimensional maze of hard surfaces and shaded niches. The growth of archaeocyathons creates vertical relief that modifies water flow, forming eddies and channels that trap organic matter. Microbial mats colonize the exposed surfaces, reinforcing the structure by precipitating fine crystals of calcium carbonate between the skeletal fragments. Over time, these mats turn the reef into a rigid mass of stone. In cross-section, the internal texture of such a reef is intricate tiny tubes, pores and chambers filled with sediments, all bound together by thin films of microbial cement. This structure will one day become limestone dense enough to survive hundreds of millions of years, holding within it the shapes of its builders. Life within and around these reefs is diverse and abundant compared to the open seafloor. Sponges of various forms attach themselves to the upper surfaces, filtering the nutrient-rich currents. Small brachiopods, shelled animals resembling clams, anchor to stable ledges and open their valves toward the passing flow. Worms bore into the softer parts of the framework, creating tunnels that later become filled with mud and minerals. Trilobites, flexible and mobile, move across the reef slopes, scavenging detritus and smaller prey. The ecosystem functions as a closed-loop plankton from the surface. Supply food animals feed and excrete bacteria, recycle waste into nutrients, and microbial films trap particles to build more stone. The entire system is sustained by sunlight-water motion and the endless recycling of material. The chemical environment within the reef is dynamic. The process of calcification consumes carbon dioxide from seawater, while microbial respiration releases it back. This balance maintains stable pH levels favorable for further mineral deposition Small changes in water chemistry can shift the rate of reef growth dramatically. When volcanic activity increases atmospheric carbon dioxide, ocean acidity rises, slowing calcification and weakening structures. When weathering on land removes carbon dioxide, the ocean becomes more alkaline and reef building accelerates. The Cambrian reefs thus act as natural regulators of the global carbon cycle, linking biological growth with atmospheric chemistry. Over decades and centuries, storms occasionally break portions of the reefs apart. Waves crash over the shallow platforms, snapping fragile branches and scattering debris downslope. Yet destruction and renewal are intertwined. The broken fragments provide new surfaces for colonization, and microbial films quickly seal cracks with fresh mineral coatings. The reef becomes stronger through disturbance, its architecture evolving toward complexity. Each collapse leads to regrowth, each fragment reborn as part of a new layer. In this way, the reef endures through cycles of calm and chaos, preserving the memory of every event within its structure. The appearance of these reefs alters more than the seafloor, it changes the chemistry of the ocean itself. By locking calcium carbonate into solid form, they reduce the amount dissolved in seawater, subtly shifting the equilibrium of ions and gases. The result is a slow decline in atmospheric carbon dioxide and a corresponding rise in oxygen. This feedback encourages diversification of life in other marine habitats. The reef is not just a physical structure, but a catalyst, a biological experiment that reshapes the planet's systems from the molecular to the global scale. Seen from above, a Cambrian reef resembles a patchwork of pale ridges and darker depressions, each outlined by shadows cast through clear water. The surrounding sea is calm, rippled only by gentle swells. Schools of tiny swimmers drift along the edges, feeding on suspended particles stirred by the currents. Light filters through the upper few meters, illuminating the complex geometry of the reef in shimmering bands. There are no corals, no fish, no familiar forms, only the quiet interplay of ancient sponges, primitive animals, and endless microbial life working in silent collaboration. The water smells faintly of lime and salt. Bubbles from decaying matter rise slowly toward the surface. Everything moves at geological pace. As the reefs continue to expand, they form chains hundreds of kilometers long along continental shelves. In time, some will merge into continuous ridges that mark the outlines of ancient coastlines. Others will remain isolated, solitary towers surrounded by open sand plains. When sea levels change, the reefs drown or are buried under sediments, yet their frameworks remain intact, transforming into massive limestone beds. These rocks will later record the rise and fall of sea level, the chemistry of ancient oceans, and the pulse of early life. In the grand rhythm of Earth's history, the Cambrian reefs represent a first attempt at permanence. Before them, life was soft and fleeting. Afterward, it begins to build enduring monuments. Each archaeocyathon skeleton is both an organism and a stone, a single body and a geological event. Their collective growth signals that biology has learned to shape the solid Earth itself. The reefs bind life to geology, turning chemistry into architecture. Their forms will vanish by the end of the Cambrian, replaced by other builders in later ages, but their influence will never fade. They teach the planet how to construct complexity and how to preserve it. In their quiet way, these early reef builders establish the pattern that will define the future life, learning to make stone, learning to hold the memory of life. Upon the growing frameworks of archaeocyathon reefs, the surface of the Cambrian Sea becomes a landscape of extraordinary detail and subtle motion. Each mound of limestone teems with organisms adapted to light, current, and shelter, forming one of the earliest examples of ecological layering. Sunlight filters through shallow water, illuminating every ridge and cavity with a soft, shifting glow. The upper slopes washed by constant flow are dominated by organisms that require movement and oxygen. Deeper recesses host species suited to stillness and shadow. The reef surface viewed up close is alive with threads, filaments, shells, and soft tissues all working in silent coordination. No single creature commands the structure. Instead, countless interactions weave stability from chaos. The archaeochaethans themselves remain the primary architects, standing in dense clusters that resemble fields of cups or fluted pillars. Their porous walls channel water inward and outward, filtering microscopic food and maintaining a constant exchange of gases. Between their skeletons, fine sediments collect, soon bound by microbial films that prevent erosion. Over this foundation, early sponges spread, anchoring to solid rock and forming soft masses that filter the surrounding water. They contribute to the reef's cohesion by trapping particles and producing additional calcium carbonate, thickening the outer crust. Each generation of growth overlays the previous one, producing a laminated record of organic construction. In cross-section, the reef resembles a tapestry woven from organisms, sediments, and chemical deposits. The uppermost layer of the reef is bright with microbial films that capture sunlight and release oxygen. Cyanobacteria dominate these surfaces, coating exposed limestone with thin sheets of green and blue. Their photosynthetic activity contributes not only to local oxygen production, but also to global atmospheric change. Within the shallow crevices, filamentous algae grow in patches, stabilizing small pockets of sediment. The entire structure operates as a living machine that converts light and minerals into mass. Even the simplest organisms play a role. Bacteria precipitate minerals that strengthen the rock, while tiny grazers feed on microbial mats, preventing them from growing thick enough to suffocate other forms of life. The reef becomes a model of balance, each process limiting another, each species holding the system within narrow physical and chemical bounds. Water movement defines the rhythm of life here. Currents sweep along the slopes, delivering food and carrying away waste. They whisper through the cup-shaped chambers of archaeochaethans, create vortices around sponges and funnel plankton into the waiting appendages of filter feeders. The strength of these currents varies with tides and weather, yet remains gentle enough to preserve structure. During calm periods, a faint drift of organic debris settles over the surface. During stronger flows, sediments lift away, exposing bare rock and fresh growth. Every cycle renews the habitat, preventing stagnation and promoting diversity. Among the fixed organisms, motile creatures navigate the complex terrain. Trilobites, agile and varied, crawl across ledges in search of detritus. Their hard exoskeletons glint faintly under the filtered light, and their jointed legs allow them to cling to vertical surfaces where softer animals cannot. Some graze upon microbial mats, scraping them away in neat paths. Others feed on smaller worms and crustacean-like scavengers. Near the reef's base, burrowing animals reshape the sediment, turning and aerating it. Tiny worm tubes protrude from the mud, their occupants extending delicate feeding filaments into the water. This subtle churning maintains the chemical equilibrium between oxygen-rich water above and anoxic layers below. Without it, decay would dominate and suffocate the reef. In the deeper recesses where sunlight dwindles, life continues in shadow. Sponges and other filter feeders form dense carpets, drawing nourishment from suspended particles rather than photosynthesis. Bacteria line the inner walls of cavities, converting waste into usable compounds. These hidden chambers serve as refuges during environmental stress, protecting their inhabitants from fluctuations in temperature and salinity. Over time, the distinction between the bright exterior and the dark interior becomes more pronounced, yet the exchange of water keeps both zones connected. Every breath of current brings renewal, and every exhalation carries recycled nutrients upward to the sunlit layers. The chemistry within the reef remains in constant flux. The dissolution and reprecipitation of calcium carbonate occur continuously as water composition changes with depth and temperature. Microscopic crystals form on surfaces where microbial activity alters local pH, turning fragile tissues into mineralized relics. Over years and centuries, these processes solidify the reef, replacing living structures with stone, while new growth builds upon the remains. This cycle growth-death mineralization ensures that the reef persists even as individual organisms vanish. In geological time, the structure becomes nearly immortal, an unbroken continuum of life and rock. Occasionally external forces intrude. A sudden storm may stir sediments from the surrounding seabed, blanketing the reef in fine mud. For a time the water darkens and the organisms slow their activity, yet within days currents wash the surfaces clean and life resumes its quiet work. Even volcanic ash settling from distant eruptions serves as new material, adding trace minerals that enrich microbial communities. Nothing in this ecosystem is wasted. Every disturbance becomes a source of renewal. The visual scene within these reefs, if one could observe it directly, would appear serene and colour-muted, dominated by soft blues and pale creams. No bright corals or fish flash across the water, only the slow undulation of sponges and the measured progress of trilobites. The silence is complete. Each living thing operates on its own rhythm, some pulsing gently with internal currents, others remaining still for months. The water is cool and saturated with suspended particles that catch the light like drifting dust. Sunbeams filter down through the clear surface, moving in slow arcs that shift with the tide, painting the reef with alternating brightness and shadow. The biological interactions here foreshadow the complexity of later marine ecosystems. Competition for space cooperation in nutrient recycling, predator-prey dynamics all appear in primitive form. The reef becomes a microcosm of evolutionary experimentation where forms of life test strategies for survival that will echo through future eras. Anchored mobile filter feeding, burrowing, every major lifestyle has a representative here. The result is an ecosystem not defined by abundance but by innovation. Each species explores a new way to live within the constraints of water, rock, and light. Over long stretches of time, reefs grow, collapse, and rebuild. Some are buried under sediments entombed in the geological record. Others continue to rise until they reach the limits imposed by light and depth. The fossilized remnants of these reefs will one day reveal the pulse of ancient oceans, each layer recording chemistry, temperature, and biological change. But within the Cambrian moment itself, these reefs exist in a steady state, a self-sustaining collaboration between mineral and organism. The living surfaces hum softly with the energy of sunlight and motion, a calm yet relentless construction of the planet's first enduring ecosystems. Here the ocean learns to build complexity in stone and to keep it alive even as time flows onward and the forms of its builders drift slowly toward extinction. Beyond the raised limestone ridges and reef-bound ledges, the Cambrian seafloor stretches outward into wide plains of soft sediment where light weakens but does not vanish entirely. Here, fine mud, silt, and sand settle in gentle gradients, forming an undulating terrain of ridges and depressions. The water moves slowly, carrying suspended particles that drift downward like snow. Each grain finds rest upon layers already compacted by time. Though the setting appears still, these plains host bustling communities of organisms adapted to life within or upon the sediment. They are quieter than the reef dwellers, less visible, yet their combined activity shapes the chemistry, structure, and stability of the seafloor itself. This is the realm of trilobites, worms, brachiopods, and other early animals that creep burrow filter and graze in the muted half-light of the continental shelf. The surface of the mud is patterned by traces of movement. Small shallow grooves mark the paths of crawling trilobites. Tiny circular pits reveal where worms have emerged to feed. These markings, preserved and buried day after day, form a living script written across the ocean floor. Trilobites are among the most numerous inhabitants here. Their jointed bodies and rigid exoskeletons allow them to move with agility across the soft substrate. They graze on microbial films, scavenge decaying material, and occasionally prey upon smaller creatures. When threatened, they curl tightly into spheres, their hard plates protecting the vulnerable underside. Their eyes, among the first complex visual organs in the fossil record, detect subtle shifts in brightness, enabling them to sense predators or locate shelter within the sediment. Worms of many types inhabit the layers below the surface. Some tunnel horizontally, leaving intricate networks that aerate the sediment. Others burrow vertically, building permanent shafts lined with mucus and clay. Through their activity, they create microhabitats for bacteria and small invertebrates, turning the seafloor into a porous living sponge. The constant mixing of mud and organic matter keeps oxygen circulating even in regions where the overlying water is poor in oxygen. These burrowers are engineers of stability. By disturbing the sediment, they prevent stagnation and ensure that chemical gradients remain balanced. Each motion, slow and repetitive, maintains the invisible infrastructure that allows more delicate life to persist above. Small brachiopods anchored by stalks dot the plains like scattered shells. They open and close their paired valves in rhythm with the passing current, filtering microscopic food from the water. Their shells, made of calcium phosphate or carbonate, gleam faintly under the dim light, and their steady feeding contributes to the continuous recycling of organic particles. Some live solitary lives. Others form loose clusters in areas where currents deliver a steady flow of nutrients. Around them, tiny crustacean-like creatures and early echinoderms move slowly across the mud, probing and sifting in search of food. Together they form a complex self-regulating community, driven by the steady fall of organic detritus from the surface waters. The chemistry of these plains is defined by balance between deposition and decay. Each day, organic matter rains from above, fragments of plankton excreta and the remains of soft-bodied animals. Bacteria in the sediment consume this material, releasing carbon dioxide, ammonium, and other compounds back into the water. Where oxygen is present, this process is slow and orderly. Where oxygen fades, sulfur bacteria take over, reducing sulfate to sulfide and staining the sediment black. The boundary between these zones shifts continually with changes in temperature, currents, and productivity. It is never fixed, always breathing in rhythm with the ocean itself. This living chemistry turns the seafloor into a dynamic system of respiration, a vast lung for the planet. The visual impression of this environment is subdued but mesmerizing. The water is cool and greenish, carrying a faint haze of suspended particles that catch stray beams of light. The sediment below is soft and smooth, interrupted by clusters of shells and the occasional mound of excreted pellets. When a current passes, the top few millimeters of mud ripple like fabric, erasing old traces and preparing the surface for new ones. The trilobites march slowly across these transient landscapes, their movements deliberate and unhurried. Worms emerge briefly before retreating. Brachiopods open and close like clockwork, while microbial mats glisten faintly in patches where they still persist. The entire sea floor moves at the pace of sedimentation, a world governed by stillness and small gestures. Occasional disturbances bring sudden transformation. When a storm rages above, waves penetrate to the bottom, resuspending mud and scattering organisms. The water cloud's visibility vanishes and currents sweep across the plains, redistributing sediments. Yet even this disruption served a function. The chaos mixes oxygen into deeper layers and spreads organic matter evenly across the shelf. Within days, the storm calms, particles settle again, and the animals resume their measured routines. Their resilience lies in patience rather than speed. Nothing in this environment relies on rapid recovery. Everything depends on continuity. Predation is present, but limited. Simple carnivores prowl the mud, annelid like worms, with jaws small arthropods that seize prey with appendages, and a few early predators that swim close to the bottom in search of movement. Their interactions are silent flashes of energy in a slow world, a quick strike, a brief struggle, and stillness once more. Most life here survives not by strength, but by strategy, burrowing, hiding, or blending with the sediment. Adaptation takes the form of endurance rather than aggression. The physical boundaries of this realm are diffuse. Toward the coast, the soft plains merge with tidal flats and microbial mats. Farther offshore, they grade into deeper basins where light disappears. Across these transitions, communities shift gradually. Photosynthetic organisms vanish first, replaced by filter feeders and detritivores. Species overlap across zones, ensuring that no boundary becomes abrupt. This continuity creates stability across the entire continental shelf, allowing ecosystems to persist even as global conditions change. Each generation of organisms contributes to the geological archive. When a trilobite dies, its shell settles into the mud and is buried by the next layer of sediment. When a worm abandons its burrow, the tunnel fills with silt that later hardens into trace fossils. Brachiopod shells, once bright and delicate, dissolve, slowly leaving imprints that record their former presence. Over millions of years, these remnants accumulate layer upon layer, forming strata that preserve the history of both life and environment. The soft sea floor, constantly in motion yet perpetually calm, becomes the memory of its own existence. Viewed in total, these plains of the Cambrian Ocean represent a triumph of simplicity. They lack the grandeur of reefs or the mystery of deep trenches, yet they host the majority of life in this time. They are the silent foundation of the biosphere, where the invisible labor of microbes, worms, and small invertebrates maintains the balance that allows the entire planet to breathe. In their quiet persistence, they demonstrate that stability itself can be an evolutionary success. The Cambrian soft-bottom communities are not scenes of spectacle, but of endurance, a world sustained by the constant interplay of decay and renewal, by the slow turning of sediment under the weight of water and time. In places where the Cambrian seas sweep across hard substrates, ancient volcanic ridges, consolidated limestone or compacted sediment, the seafloor transforms from soft mud into a landscape of stone. These areas, known as firm grounds, provide stability in a world otherwise shifting and eroding. They resist the slow rearrangement of currents, offering rare surfaces for attachment and permanence. Upon these stable platforms, new forms of life take hold, fastening themselves to rock, extending upward into the water, and filtering the passing currents for nourishment. The creatures that inhabit these firm grounds live without shelter or concealment. They are fixed to their foundation, dependent on the rhythm of the sea around them, each adapted to withstand constant exposure to moving water. The first colonizers of these hard surfaces are sponges and early sessile organisms. Their bodies simple yet efficient anchor tightly to the rock by basal pads or cement-like secretions. Each sponge draws water through countless tiny pores, filtering microscopic food and releasing clear water back into the ocean. Their shapes vary according to current and light. Some form low encrusting mats. Others grow into small chimneys or hollow tubes. In quiet water they rise tall and slender, but in stronger flow they remain flat and compact to resist breakage. Over time their skeletal remains accumulate, forming crusts of silica and calcium carbonate that strengthen the surface for future generations. Around them, bacteria and algae coat the rock with a thin film that glows faintly under the filtered sunlight, adding colour to the grey foundation. Attached among the sponges are brachiopods, their shells curved and symmetrical, each anchored by a flexible stalk that extends into a crevice. They open and close rhythmically, drawing in water and filtering suspended particles. Their delicate feeding structures, the lopophores, wave within the gentle current, capturing plankton and organic debris. Their shells are thin but resilient, able to endure the slow rain of sediment and the brushing of passing animals. Some species cluster in dense patches that form miniature meadows upon the stone. Their combined feeding activity stirs the water, enhancing local circulation and preventing stagnation. The rhythmic motion of hundreds of shells opening and closing in unison gives the impression of a living field breathing with the tide. Echinoderms, distant ancestors of starfish and sea urchins, also appear among these firm grounds. Early stalked forms, precursors to crinoids, anchor by flexible stems that allow their cup-shaped bodies to sway gently. Their feathery arms extend into the water to intercept food. Unlike the mobile trilobites of the muddy plains, these echinoderms remain rooted, dependent on constant flow. They occupy higher positions on the rock, exposed to turbulence that brings both risk and reward. The movement of water through their arms not only delivers food, but also keeps sediments from settling. In the dim light, their calcareous skeletons glimmer faintly, contributing to the quiet shimmer of the seafloor. Between these stationary organisms, the rock surface becomes home to minute grazers, early mollusks, primitive arthropods, and other small animals that scrape biofilms and bacterial mats from the stone. Their feeding tracks trace winding paths across the substrate, each marking a slow search for sustenance. Some bore into the rock or into dead sponge skeletons, creating protective cavities that become homes for generations. The interplay between the fixed and the mobile, between construction and erosion, gives the firm ground community its characteristic texture. It is neither static nor chaotic, but an intricate equilibrium maintained by countless tiny interactions. The water above these communities is clear and steady, enriched by oxygen from nearby shallows. Currents pass continuously, sometimes strong enough to bend flexible stalks, and fan out sponges like soft corals. Every few minutes, particles of detritus drift by, captured by filtering appendages and transferred into digestive chambers. No organism here moves quickly, yet together they process vast volumes of water each day. The collective effect is purification. Sediment settles elsewhere, while these benthic filters keep the surrounding sea clean and transparent. Over time, the accumulation of skeletal debris cements the environment even further. Dead shells and spicules become part of the substrate, turning living surfaces into rock. This slow feedback loop reinforces the stability of the entire system, making it more resilient to change. Occasionally, fine sediments carried from distant rivers settle over these communities. If the deposition is light, the animals survive, simply extending upward or brushing the particles away. If it is heavy, the layer suffocates them, sealing the living rock beneath mud. Yet even in death, they contribute to the next generation. Microbes colonize the buried surfaces, decomposing organic remains and precipitating minerals that bind sediment to the stone below. When conditions clear again, new organisms attach to the hardened crust, continuing the cycle of colonization. This alternating rhythm of burial and exposure transforms firm grounds into layered archives of biological construction, each layer representing a brief pulse of stability in an ever-changing sea. Light in these areas varies with depth. In shallower zones where sunlight still filters through microbial mats, add color greens, browns, and purples that mark zones of photosynthesis. Deeper down the world fades into shades of blue-grey, lit only by refracted light from the surface. The contrast between illuminated ridges and shadowed crevices creates patterns across the seafloor, subtle gradients that determine where each species can thrive. Animals that depend on photosynthetic films remain near the bright edges. Those that filter feed dwell in shaded recesses where currents concentrate particles. The spatial organization of life follows the physics of light and flow, a natural architecture formed without intention. The chemical processes underlying this ecosystem are slow but profound. The combination of biological growth and mineral precipitation transforms the seafloor into a patchwork of hard grounds that resist erosion. Calcium carbonate secreted by organisms and precipitated by microbes forms thin veneers that glue shells and skeletons together. Trace elements such as magnesium and iron infuse the rock, altering its color and composition. Over millions of years, these deposits accumulate into stratified limestones that preserve the minute details of shells and spicules. In these stones, the fine geometry of life endures far beyond the lifespan of any individual organism. From a distance, a firm ground community resembles an underwater meadow sculpted in slow motion. The stationary forms stand like plants in an invisible breeze, their motions synchronized with the pulse of the sea. Tiny animals move among them, creating trails that intersect and vanish as sediment drifts. The entire scene unfolds in silence, the only sound the faint crackle of water moving through pores and channels. The atmosphere is one of calm persistence, a world balanced between fragility and endurance. Nothing here happens quickly, yet everything happens continually. Through this union of life and stone, the Cambrian firm grounds introduce a principle that will echo throughout Earth's history: the transformation of living activity into geological permanence. Each anchored organism adds a layer of material to the planet's crust. Each generation builds upon the last. Over time, what begins as a simple attachment becomes the foundation for future life. The stable seafloors of the Cambrian thus mark a turning point. Life no longer merely adapts to the solid Earth, it begins to shape it, to turn biology into architecture. In this quiet partnership between creature and substrate, the planet's long conversation between the living and the mineral truly begins. Above the tranquil seafloor and beyond the slow realm of reefs, an open blue expanse stretches across the Cambrian world, a column of moving water filled with creatures that drift, swim, or glide between layers of light and darkness. It is a fluid domain without boundaries, where gravity is balanced by buoyancy and motion replaces permanence. Here in the mid-water, the first true swimmers evolve, joining the countless drifters that have floated since the dawn of multicellular life. Every particle, every living cell moves as part of a vast suspension that circles the planet in silent continuity. At the smallest scale, plankton dominates this space. Countless microscopic organisms drift with the currents, unable to swim against them. Some photosynthesize near the sunlit surface, forming a green veil that converts light into chemical energy. Others, heterotrophic and transparent, feed upon them, forming the foundation of the food web. These drifting cells reproduce rapidly, dying just as fast, their remains falling like snow toward the depths. Together they create the rhythmic pulse of the ocean's metabolism, sustaining all larger forms that depend upon them. Each cubic meter of water teems with millions of these invisible architects of life, transforming sunlight and minerals into the fuel that drives the biosphere. Among this microscopic rain move larger creatures, nectonic animals capable of directed motion. The most familiar of these are the trilobites that have left the seafloor to swim freely, using their fringed appendages to paddle slowly through the water. Their movements are graceful and rhythmic, their hard exoskeletons refracting the dim light in soft metallic hues. Some rise toward the surface during the night, and descend again by day following vertical migrations that mirror the shifting gradients of light and temperature. Others remain suspended in mid-water, gliding horizontally in search of food, their compound eyes, adapted for detecting contrast rather than colour, track the faint silhouettes of prey or rival. In this vast open space, encounters are infrequent, yet each one shapes the subtle evolutionary contests that define early marine life. Among the trilobites drift other arthropods, some with elongated bodies and flexible limbs, others with flattened forms that cut smoothly through the water. Their propulsion is slow but continuous, achieved by the coordinated beating of appendages or gentle undulations of the body. These early swimmers are not predators in the modern sense, but opportunistic feeders, filtering suspended matter or scavenging detritus. A few, however, begin to specialize. Streamlined forms develop slender, tapered bodies with fin-like extensions that reduce drag. These animals mark the beginning of active pursuit and escape the first faint outlines of the predator-prey dynamics that will later dominate ocean life. The chemistry and physics of this open sea determine who survives. The upper 100 meters are warm and oxygen-rich, while deeper layers grow cooler and depleted. Currents act as invisible highways transporting nutrients and organisms across great distances. In regions where surface water sinks oxygen and organic matter travel downward, feeding deep communities. Where deep water rises, nutrients return upward, fueling productivity near the surface. The ocean circulates like a living lung, and the drifters within it are both passengers and participants. Each species occupies its own narrow range of temperature, light, and nutrient concentration, forming invisible layers stacked one upon another, a vertical tapestry of life woven through time. The appearance of larger predators changes the rhythm of this realm. Anomalocaridids, elongated animals with paired swimming flaps and grasping appendages, emerge as the most formidable swimmers of their age. They move with sinuous grace, propelling themselves by undulating fin-like lobes along their sides. Their eyes, large and compound, detect motion with remarkable precision. They patrol the water column, hunting smaller arthropods and soft-bodied animals, seizing them with spined claws and tearing them apart with circular mouths lined with hardened plates. Despite their dominance, they are rare. Their size and energy demands limit their numbers, yet their presence introduces a new ecological dimension fear. The smaller drifters respond not with awareness but through evolution, adopting shell spines and new body plans that provide defense. The slow arms race of adaptation begins here, suspended in the blue space of the Cambrian Ocean. Near the surface, gelatinous creatures drift in endless motion, their transparent bodies illuminated by refracted light. Some resemble flattened bells or sacs, others trail filaments that capture organic particles. They're not yet true jellyfish, but early experiments in buoyancy and passive feeding. Their bodies, composed mostly of water, move rhythmically with contractions so gentle they barely disturb the surrounding fluid. Beneath them, clouds of detritus swirl in slow eddies, feeding smaller filter feeders that trail below like living nets. The interplay of drifting forms and sinking debris turns the water column into an ever-turning conveyor of matter and energy. Sound does not carry far in this world of soft tissues and low energy. Communication, if it exists, occurs through vibration and current. The water is neither silent nor noisy, but filled with constant motion, the gentle rise of bubbles, the faint crackle of organic decay, the rhythmic pulses of swimming bodies. Light fades gradually with depth, and the colours shift toward blue-grey. As day passes into night, the surface cools slightly, and plankton ascend toward the warmth, drawing their predators behind them. Each dusk triggers a slow migration upward, each dawn a descent. This cycle continues unbroken, a planetary breathing that never stops. The mid-water ecosystems of the Cambrian differ from anything that will follow. There are no fish, no vertebrates, no large schools or rapid chases. Life here moves in slow spirals guided by instinct and physics rather than intelligence or strategy. The largest swimmers measure less than a metre, yet to the microscopic world they are giants. Their feeding, swimming and dying reshape the chemistry of the ocean, redistributing oxygen and carbon. When they perish, their bodies sink, carrying nutrients to the deep and leaving trails of decay that feed the benthic realms below. In this way, the vertical circulation of matter connects all levels of the sea, from sunlight to darkness, from life to sediment. Occasionally, environmental changes sweep through this open realm. Volcanic eruptions release ash that settles through the water, briefly shading the surface and reducing light for photosynthesis. Productivity declines, oxygen levels drop, and many swimmers descend to cooler depths in search of stability. Yet within a few years, the system recovers, driven by resilience rather than speed. The continuity of oceanic circulation ensures renewal even after disruption. The equilibrium of this world depends not on constancy, but on its capacity to absorb change. Seen from above, the Cambrian Sea appears as a shifting mosaic of blues and greens, its surface rippled by the wind but its depth serene. Within that fluid immensity, countless beings drift and swim, each contributing to the slow unfolding of life's story. None understand their place yet. Together they form the foundation of all future marine ecosystems. The open ocean of the Cambrian is both laboratory and archive, a dynamic field where evolution experiments with motion, form and interaction. Here life first masters the art of suspension, living within water, not as passengers but as architects of its movement. Everything below on reefs and plains depends upon this upper world of swimmers and drifters. Their invisible labour fills the ocean with energy, turning sunlight into motion and motion into memory. In the quiet blue heart of the Cambrian Sea, the lineage of all future ocean life begins to move with purpose, slow but unstoppable. Beneath the visible world of swimming creatures and reef-bound colonies lies another realm, one far smaller yet equally intricate. The Cambrian explosion does not exist only in the scale of animals and ecosystems, it also unfolds within the very architecture of life itself. Every shell spine and fragment of tissue emerging in this age is the result of chemical precision and microscopic innovation. Under magnification, what appears simple becomes a city of structure, fibers, lattices, crystals and membranes forming ordered patterns unseen by the naked eye. The development of mineralized skeletons, hard parts composed of calcium carbonate, calcium phosphate or silica, represents one of the most consequential transformations in Earth's biological history. The shift from soft tissue to durable frameworks alters the planet's chemistry, its sedimentation, and its fossil record. In the Cambrian seas, countless microorganisms already manipulate minerals to their advantage. Cyanobacteria precipitate fine layers of carbonate that form stromatolites, building mounds of limestone grain by grain. Diatom-like and radiolarian-like forms, though still primitive, begin to incorporate silica into their cell walls, testing new ways to combine biology and geology. For the first time, evolution favors the ability to construct durable surfaces, shells, plates and spines that both protect and support. Within the cellular machinery of early animals, ions of calcium and phosphate move through controlled pathways guided by proteins that dictate crystal growth. These molecular processes take place in silence within the cytoplasm of tiny cells, but their cumulative effect changes the composition of oceans and sediments alike. The sea itself becomes saturated with the byproducts of biological construction, turning into a vast reservoir of dissolved minerals awaiting incorporation into new forms. In trilobites, the exoskeleton represents the peak of this early mastery. Each plate is composed of calcite crystals arranged in precise alignment, giving both strength and transparency. The layers of the shell vary in density, thicker where stress is greatest, thinner where flexibility is needed. The eyes of trilobites, built from the same mineral, are compound structures made of hundreds of tiny lenses, each an individual crystal of calcite oriented to focus light accurately into the underlying sensory tissue. Nothing like this has existed before. Vision itself becomes a geological process where stone refracts light for the benefit of life. The refinement of such structures requires a balance of chemistry and biology that the Cambrian seas uniquely provide. High concentrations of calcium and bicarbonate ions make mineral precipitation energetically easy, while microbial ecosystems maintain local pH conditions that favor stability. The entire planet participates in the creation of these intricate designs. Sponges too reveal the new intricacies of form. Their bodies, once gelatinous, now incorporate silica spicules, microscopic rods and stars that support the porous framework. Each spicule grows from a central organic filament, where minerals deposit in concentric layers, guided by proteins that regulate shape and orientation. The result is both functional and beautiful skeletal elements that scatter light and strengthen the animal without sacrificing flexibility. In later ages, these spicules will accumulate into cherts and siliceous sediments, preserving evidence of organisms long vanished. Even as they live, they prepare their own fossils, ensuring continuity between the biological and geological realms. Brachiopods and other shelled organisms follow different chemical paths. Many use calcium phosphate, forming dense shells resistant to dissolution. Others rely on aragonite, a more soluble but easier to precipitate form of calcium carbonate. The diversity of mineral choices reflects the variability of seawater chemistry across the Cambrian world. In warm, shallow lagoons, carbonate saturation is high, promoting rapid shell growth. In cooler or deeper waters, phosphate dominates, creating sturdier but heavier structures. These variations imprint the environment directly into the body of each creature, so that every shell becomes a chemical diary of its surroundings. The ratio of isotopes locked within them records temperature, salinity, and even the composition of the atmosphere at the time of growth. Through this interplay, life begins to write its own physical history in stone. The evolution of mineralized tissue also transforms the ecological landscape. Hard surfaces allow for new behaviors, boring, drilling, grasping and cutting, that were impossible in a soft-bodied world. Predation becomes more efficient, defense more elaborate. The rise of shells leads to the rise of claws. The emergence of skeletons gives purpose to movement. Within the protective armor of calcium carbonate, muscles can attach and contract with greater force, enabling stronger motion. Limb segments and appendages evolve as frameworks of leverage. This mechanical revolution takes place invisibly, one microstructure at a time, yet it reshapes the direction of evolution for all future life. At the scale of molecules, these changes ripple outward into the ocean's chemistry. The extraction of calcium and carbonate from seawater alters its balance, lowering saturation in some regions and increasing sedimentation on the seafloor. Newly formed skeletons eventually dissolve after death, returning their components to circulation, creating a continuous cycle between life and mineral. The ocean becomes a self-sustaining factory of stone with organisms as both engineers and products. The sediment that accumulates during this time is distinct, fine-grained rich in biogenic material layered with microscopic fragments of shell and bone. Over millions of years, these deposits will harden into limestone that captures not just shapes, but the molecular fingerprints of its makers. Even soft tissues, though rarely preserved, reveal remarkable complexity in the Cambrian. Under exceptional conditions, thin films of carbon-outline muscles, guts and sensory organs in fossil beds that will one day astonish paleontologists. These remnants confirm that the hidden machinery of life has already achieved extraordinary sophistication. Nervous systems, circulatory pathways, and digestive tracts operate within fragile bodies that float or crawl through the ancient seas. Each represents an experiment in organization, an attempt to coordinate movement and sensation. The evolution of hard parts merely renders these invisible systems more resilient to time. Microbial life, omnipresent and tireless, plays a quiet supporting role in all of this. It mediates mineral formation, recycles organic matter, and stabilizes sediments. In some regions, bacterial films grow directly upon shells, secreting minerals that repair cracks or reinforce weak spots. In others, decay microbes decompose soft tissue after death, guiding the transformation of flesh into fossil. The partnership between bacteria and animals, though unspoken, defines the durability of biological remains. Without these microbes, most of the Cambrian structural innovations would vanish without a trace. At this scale, beauty arises from geometry. Under magnification, the skeletal elements of Cambrian organisms appear as repeating lattices, spirals, hexagons, honeycomb arrays, each obeying chemical laws rather than artistic choice. The symmetry of nature expresses itself in every crystal and fibre, producing efficiency through repetition. These forms anticipate the architecture of future corals, shells, and bones. The Cambrian Ocean thus becomes a workshop of pattern, where evolution learns to use chemistry as design. Every species contributes its own experiment, and through them, the planet's mineral record becomes a vast museum of invisible art. The legacy of these microstructures endures beyond the era itself. When the organisms die, their remains settle gently onto the seafloor, merging with mud and sand. Over time, pressure and heat transform them into stone, preserving in atomic detail the blueprint of early life. Long after the species disappear, their architecture remains intact, testifying to the moment when biology and mineral first fused. The Cambrian explosion viewed from the molecular level is not a sudden burst, but a slow crystallization, a gradual encoding of life's design into the fabric of Earth. Every shell fragment, every spicule, every microscopic lens becomes part of that message. In the quiet depths of the ancient sea, the hidden microstructures of life begin to carve their permanence into time itself. Across the Cambrian seas, life and death form a single unbroken loop. Every organism that grows, swims, or clings to rock eventually returns to the same quiet floor from which it came. The ocean, though vast, is a closed system where energy passes endlessly from one form to another. In this age, before plants, before forests, and before vertebrates, the processes of decay and burial already shape the surface of the planet. The rhythm is steady and impartial. Light nurtures growth in the upper layers. Gravity draws the remains downward. Chemistry transforms them into stone. Through this cycle, the living world begins to write its enduring history in the strata of the Earth. When an organism dies, whether drifting plankton or sturdy trilobite, its body enters the slow choreography of decomposition. In the warm oxygenated shallows, bacteria act quickly, breaking soft tissues into simpler compounds. Carbon dioxide and ammonia diffuse into the surrounding water, enriching it for future life. In deeper or stagnant areas where oxygen runs thin, the process changes. Sulfate-reducing bacteria take over, consuming organic matter and releasing hydrogen sulfide that reacts with iron to form dark pyrite. The smell, were one able to perceive it, would be sharp and metallic. Each zone of the ocean carries its own form of decay, and together they maintain the chemical balance that allows the biosphere to persist. The very act of dying sustains the living. As decomposition proceeds, the remaining structures, shells, spicules, and bones begin their descent. They drift slowly through the water column, accompanied by flakes of organic debris and mineral dust. This continuous shower of material, sometimes called marine snow, links every layer of the ocean. Each particle moves at its own pace. Fine clay takes years to settle, while dense shells reach the seafloor in days. During descent, many fragments dissolve or are consumed by scavengers, but enough survive to build a steady blanket of sediment across the ocean floor. Over millions of years, this rain of death becomes one of the most powerful geological forces on Earth. On the seafloor, the cycle continues. Newly arrived remains encounter the chemistry of the sediment, where microbes and minerals collaborate in transformation. Organic carbon becomes bound within clay, shells compact under their own weight. Voids fill with minerals carried by pore water. The earlier steps of fossilization begin almost immediately. In some places, anoxic conditions preserve fine details, the outlines of limbs, the impressions of eyes, even traces of soft tissue. Elsewhere, stronger currents or oxygen-rich water destroy delicate features, leaving only fragments. The difference between preservation and erasure depends on subtle balances of oxygen, temperature, and chemistry. The Cambrian world, through its diversity of environments, produces both. Reefs play a special role in this cycle. When storms break their upper surfaces, fragments of archaeocyathans and sponges tumble into deeper water, creating debris slopes at the base of each reef. These fragments are quickly buried in fine carbonate mud and cemented into limestone, forming solid records of biological construction. In other settings, the remains of soft-bottom communities accumulate more gradually. Layers of mud alternate with thin sheets of sand marking pulses of calm and turbulence. Each layer captures a moment in time: storm season, volcanic eruption, quiet year. The planet's first detailed calendar is written not in symbols but in strata. Over generations, sediments compact and harden. The weight of overlying layers squeezes water from the pore spaces, increasing pressure and temperature. Chemical reactions rearrange minerals, turning mud into shale lime, into stone organic matter, into carbon films. The transformation is slow but relentless. Within a few million years, the living ocean becomes an archive of itself. The bones of trilobites, the spicules of sponges, the shells of brachiopods, all become pages in a vast geological record. The sea is not only a habitat, it is a writer pressing the memory of its creatures into the fabric of the earth. Yet burial is not always permanent. The same forces that create rock also lift and expose it. As tectonic plates shift, seafloors rise to become land. Sediments erode, releasing ancient carbon back into the atmosphere. What was once death becomes the source of new life. The cycle extends beyond biology into the planet's own metabolism. Carbon buried in limestone regulates global climate by removing greenhouse gases, when those rocks weather the carbon returns, balancing warmth and cooling over eons. Through this endless exchange, the Earth breathes. The Cambrian Ocean, in establishing this rhythm, sets the foundation for all subsequent climates and ecosystems. The visual impression of this process is deceptively calm. On the seafloor, nothing appears to happen quickly. A trilobite carcass rests motionless as thin films of bacteria spread across it. Fine grains of silt settle into its joints. Within days, its soft parts collapse, leaving the rigid shell half buried. Over months, mineral-rich water seeps through, depositing tiny crystals that fill internal spaces. After centuries, the sediment above compresses into stone, sealing the fossil within darkness. For the next 500 million years, it will remain undisturbed, waiting for erosion or tectonic uplift to bring it once again into the light. The story of life written in stone begins with such ordinary events repeated across the sea. Not all remnants become fossils. Most decay, completely returning their atoms to circulation. This recycling ensures that the ocean never runs out of the materials needed for growth. Calcium, carbon, phosphorus and nitrogen cycle through countless generations, linking the smallest microbes to the largest swimmers. Death in this sense is not an ending, but a phase in continuous transformation. The boundary between living and non-living matter is porous. The same molecules that form a trilobite's shell may later become part of a reef, a plankton cell, or a new organism entirely. In this ceaseless turnover, the ocean achieves immortality even as individual lives remain brief. Occasionally, catastrophic events accelerate these processes. A sudden influx of sediment from a storm or underwater landslide can bury entire communities in an instant. The lack of oxygen halts decay, preserving details otherwise lost. Such episodes become time capsules within the rock record snapshots of ecosystems frozen at the moment of disaster. Though destructive, they are also generous, giving future worlds their clearest glimpses into the past. The Cambrian seas, with their mix of stability and upheaval, produce many such windows. The longer view reveals balance rather than chaos. Over tens of millions of years, rates of sedimentation, erosion and burial equalize. Life expands, dies and regenerates in synchrony with geological change. The planet's crust thickens with the weight of its own history, while its surface remains vibrant and mutable. The interplay of growth and decay transforms the ocean from a passive container into an active participant in evolution. Every grain of sediment, every mineral, every atom of carbon carries the imprint of countless lives that preceded it. By the end of the Cambrian, this cycle of growth, death and burial has become an unbroken thread connecting the biosphere to the planet's deep interior. The ocean's floor, layered with the remains of generations, tells of both abundance and loss. What began as simple chemical reactions now sustains a planetary rhythm production, in the light decomposition, in the dark preservation in stone. The sea endures as both cradle and grave, endlessly renewing itself through the quiet exchange of matter. In this world of slow transformation, permanence arises from impermanence, and the memory of every life becomes part of the Earth itself. As the Cambrian period reaches its quiet middle age, the planet settles into a steady rhythm of light motion and time. The continents have drifted into familiar positions, Gondwana vast and southern Laurentia and Baltisa, wandering nearer the equator, and the oceans between them shimmer under a sun now slightly stronger than in the eons before. From the upper atmosphere to the deepest mud, Earth breathes through its seas. Every current, every tide, every cloud of plankton contributes to a balance that holds the planet in gentle equilibrium. There is no sound of wind in the great depths, no breaking of waves beyond the continental shelves. The world is almost completely ocean wrapped in soft air and quiet light, a planet of calm vitality. From far above, the Cambrian earth would appear blue beyond imagination. The shallows gleam turquoise, the open basins deep cobalt. Thin streaks of white cloud drift across the sky, and round the equator belts of brighter water mark regions of intense photosynthetic life. Along the margins of continents, bands of pale green trace the shallow seas, where reefs and microbial mats spread like living skin. These are the centres of activity, but even here change is measured in years rather than hours. The waves roll in endless sequences, each one nearly identical to the last. The continents themselves are bare and silent, their coasts eroding slowly into the sea, feeding the chemistry that sustains life. Beneath the surface, the water column forms a vertical universe of stillness layered by light. Near the top, the brilliance of day nourishes the drifting plankton that fill the ocean with energy. Below, the faint blue twilight holds swarms of slow-moving animals that rise and fall with the rhythm of the sun. Deeper still, the darkness remains constant, punctuated only by the faint glow of bioluminescent microbes and the invisible pulse of chemical reactions. The temperature changes little from year to year, the salinity almost never. Everything is suspended in balance. The planet has reached a kind of ecological harmony, where evolution proceeds quietly, not in bursts, but in steady elaboration. On the continental shelves, reefs continue their slow construction, reaching upward centimetre by centimetre, adding new layers of stone to the old. The archaeoceathans, once abundant, are beginning to wane, replaced gradually by sponges and other builders. The limestone masses they leave behind form natural breakwaters, protecting lagoons where sediments accumulate and fine creatures thrive. Around their slopes, trilobites crawl in abundance, their exoskeletons glinting faintly in the filtered sunlight. Brachiopods cluster nearby, opening and closing their shells with the tide. Worms trace invisible paths through the mud, recycling the detritus that falls from above. No event is dramatic, yet every motion contributes to a global continuity that will persist for tens of millions of years. The air above these seas contains more oxygen now than at the dawn of the Cambrian, enough to alter the chemistry of rocks and rivers, enough to make the skies bluer and the storms more temperate. Volcanic eruptions still occur, but less frequently. When they do, their ash spreads thinly across the ocean, providing nutrients that spark brief surges of productivity before settling quietly into the sediment. The climate remains warm but stable, moderated by the vastness of the sea. No glaciers form, no deserts expand. It is a greenhouse world governed by water, sunlight, and time. The rhythm of the tides, shorter than in later ages due to the moon's nearness, creates a cadence that underlies every process. Each day brings 2 slow pulses of the ocean's breath, an eternal measure against which all life moves. The creatures of this world know nothing of extinction or permanence. Their existence is immediate bound to the gentle physics of their surroundings. Plankton drift and divide their lives, lasting only hours. Trilobites molt and grow, leaving empty shells behind them as records of passing time. Sponges filter water in unending patience, turning microscopic particles into living tissue. Predators, still rare, glide through the dimness in search of motion. The balance between creation and consumption remains delicate but stable. Life does not yet fill every niche. Vast spaces of the ocean remain empty, waiting for future forms to inhabit them. Yet within the Cambrian stillness, the foundations of complexity are firmly set. The seafloor viewed in cross-section resembles a layered memory of the age. Each horizon of limestone shale and sandstone records a moment of the planet's breathing. The fine laminae of mud capture the trails of worms. Thicker beds preserve the impressions of reefs and shells. Over time, these layers will harden into the enduring pages of geology, storing the story of a world both dynamic and serene. The composition of these rocks will influence all that follows, determining how continents erode, how mountains form, how carbon cycles between land, ocean, and air. In its quiet way, the Cambrian Earth is already shaping the deep future. If one could stand upon a shallow ridge within these seas, the scene would appear dreamlike. The water, clear to great depth, would reveal a world of muted colour and slow movement. Pale sponges rise like towers. Trilobites move in small processions along the sand. Clouds of plankton shimmer where sunlight breaks through. Occasionally a larger swimmer passes its body, casting a shadow that ripples downward. The temperature is warm, but even the currents steady the pressure of water, embracing everything equally. Sound is absent except for the distant rumble of tides against unseen coasts. Above, faint streaks of white mark the reflection of clouds, while beneath a dim gradient of light fades smoothly into blue-grey silence. The entire biosphere exists in a state of poised evolution. Genetic variation accumulates slowly, giving rise to forms both intricate and strange. Eyes refine, limbs articulate, shells diversify. Every organism carries within it the chemical and structural lessons learned from countless predecessors. Each innovation ripples outward through ecosystems, adjusting balances and creating opportunities. Yet nothing in this world rushes. Even the evolutionary pace, though accelerating relative to the ages before, unfolds in the rhythm of geological time. The Cambrian stillness is not absence of change, but its purest form transformation, distributed across millions of years, too slow to disturb the calm of any single day. At the planetary scale, the Earth of the Cambrian hums with quiet stability. Carbon dioxide and oxygen maintain an even ratio. The ocean's circulation moves heat efficiently between equator and pole. The absence of land plants means erosion remains unimpeded, continually feeding minerals to the sea and sustaining the carbonate cycle. Clouds form and dissipate with predictable frequency, their patterns influenced by slow atmospheric currents. Even the moon, though closer and brighter, moves steadily outward, its pull-shaping tides that have persisted since the beginning. Everything within this world is in conversation, air with water, with rock, with life. As time drifts forward, the Cambrian period approaches its end. The reefs thicken, continents shift, and species evolve beyond recognition. Some vanish quietly, leaving fossils buried beneath new layers. Others diversify into forms that will dominate later eras. Yet the essential mood of the planet remains unchanged, tranquil, balanced, and self-sustaining. The light of the young sun falls evenly across the ocean, and the world turns unhurried beneath it. There are no forests, no birds, no sounds of breaking waves on populated shores, only water, stone, and life existing in endless equilibrium. In the stillness of this age, Earth completes its transformation from chaos to order. The planet that once glowed with molten rock now supports a tapestry of breathing organisms. The chemistry of the atmosphere, the circulation of the seas, and the structure of life have become linked in one great system of reciprocity. Every shell and crystal, every ripple and current contributes to that unity. The Cambrian world, viewed as a whole, is neither beginning nor end, but balance itself a long, quiet interlude, in which the foundations of complexity have settled firmly into place. The ocean glows faintly in the sun, the continents rest in silence, and the planet turns patient and alive, carrying within it the memory of light.